Okay. Yeah. Good afternoon, everybody. Thanks for coming again. Today, I see some familiar names, but one new name. So I have to go through the spiel one more time. Sorry for you, everyone who's heard it before. But what we're doing today basically is an opportunity for you to see some of the cool projects that are going on this summer with the Summer Community of Scholars research program, undergraduate research program here at UAH. So um, this is a program that undergraduates can apply for. So I don't know if all or any of you are planning to come to UAH this fall, but this program has been going on for a while, and it's an opportunity to work with one of our faculty or researchers over the summer semester. So it's a 10-week program, and we provide a stipend to the student. Stipend is, it's not like salary. It's not like you're a job where you're doing some work and getting paid. But a stipend is money to help you offset cost of living, like paying your rent or buying food, buying gas, stuff like that, so that you can participate without having to have a part-time job, basically. So you can just focus on the research all summer. So it's a really good opportunity, especially if you like those kind of hands-on things. It's definitely what you're doing. So today we have Nicholas Johnson, one of our students, who's been doing this project with Dr. Lay in our chemical and materials engineering. Is that the right?
Yes.
And so I know nothing about this. So I'll let Nicholas introduce himself and describe the project to y'all.
All right. Hey, everyone. I'm Nicholas Johnson with the Chemical Engineering Department. And my RCU project this summer is about metal organic frameworks. And if you read the blurb I wrote up about it, I think I talked about carbon dioxide capture, which is not what we ended up, is not what we're going to do. We're going to do essentially adsorb methylene blue, which I'll talk about a little bit later. It's a dye that's in wastewater that we plan, or that scientists in general are trying to get rid of, or find new ways to get rid of it.
So yeah, Nicholas and I had talked a little bit before you guys came on. And this happens sometimes in the research, like what's proposed for the summer and what happens sometimes will change. This time, this has happened. Maybe some of you saw Dr. Canistris, his presentation, that the chemicals that they ordered to do this research, didn't come because they were delayed by COVID. And so, yeah, they basically kind of had to make a decision maybe and change, their focus a little bit. Slightly. So since the time they submitted this, as Nicholas said, maybe the focus has changed a little bit, but it's still, it's still all research. It's just like sometimes you have to do that in research where something's not working right, or you don't have the thing you need, so you have to, change slightly. So this is a good example of that.
All right. Can you go to the next slide? All right, so I wanted to start off by talking about what even is a metal organic framework in the first place. That's what when I first came to UAH, one of the very first things I want to do was get started in research right away. And I think this was one of the projects that was proposed that caught my attention. And thankfully, I got a chance to work on this, although it's a long time in the making because of COVID delayed my first project.
So what year are you now, Nicholas?
I'm going to become a junior next year, but
Okay.
I actually applied for this exact project freshman year, and I was accepted into it. But then COVID happened, so it's delayed a year.
Gotcha.
And now we have more delays, but don't worry about that.
You're finally working on it, though.
There we go. So I included on the slide a really high-level explanation that I took from a dissertation. And I also included a diagram. But what a metal organic framework is, it's essentially composed of, you have metal ions and organic linkers that bind them together. And the metal ions are positively charged, I should mention that. And the metal organic framework itself is hollow. And that's what caused it to have a fairly large surface area, or relatively large surface area. And MOFs were first synthesized 90s or so, and ever since then there's been thousands of them, and there's being investigated for many different applications, as I just mentioned, water treatment or CO2 capture in the International Space Station is certainly one of them. There are things just like sensors, catalysts in general, gas storage and filtration, and also carbon dioxide capture. And I found a paper the other day, which was about using biological-based metal organic frameworks for that. And that's where, so you have the metal oxides, but instead of the organic ligand would be replaced with like a biological molecule, essentially like a protein or something like that, which is, I'd never heard of that before. That was really cool. And the last student in Dr. Lay's lab, that's the professor I'm working with, used a metal organic framework called ZF8. And what they were studying was oxidative dehydrogenation of ethane to produce ethylene. It's a bit complicated, but essentially analyzing the reaction conditions of that. Next slide, please. Now, what the metal organic framework we are studying is called UIO 66, a zirconium-based metal organic framework. And there's a whole bunch of these, but this one is quite stable and pretty easy to synthesize. And what we plan on doing is, well, before I get into that, the typical synthesis of UIO 66 is with, you have the same amounts of zirconium chloride and what's called teraflactic acid. That's the ligand part. And you use a solvent, I think it's, what is it called again? Dimethylformamide. You probably have seen it abbreviated as DMF. Actually, maybe not, but you will. And you would put that in a vessel for 24 hours at 120 degrees Celsius or so. And that's how, the figures I'm reading off are from a scientific paper. I think the very first one that synthesized UIO 66. And then when crystallization happens and they analyze the surface area, they found it to be a very high number, like 1,000 something meters squared per gram, which is pretty insane if you think about it. But then again, the materials are exceedingly small. And another thing with metal organic frameworks is that you can use a modulator to essentially slow down the crystallization process I previously mentioned, to essentially control the growth of it. And another thing that they can do is create what are called defects. And what these defects can do is increase the surface area and other properties, but at the same time, they can reduce the stability of it. So it's kind of like a balancing act. It's like, all right, how much do we want to increase this property, but without actually destroying the molecule itself or something to that effect. And for UIO 66 with the teraflactic acid, I think you can see that on that image. I think where it's blown up, and I think there's a diagram where it shows where this hydrogen attached that little ring, benzene ring. And you can replace one of those hydrogens with a different group in chemistry, a functional group. And the one we use, what we plan to use is sulfur as a sulfur-based functional group. And the reason why we want to do that is this sulfonated UIO 66 was found to adsorb dyes, particularly methylene blue, much better than UIO 66. And I believe I mentioned that's ion selective. What I mean by that is that it essentially completely absorbed positively charged dyes and rejected the negatively charged ones. And I think the original paper was published very, very recently. They went through a whole bunch of these different dyes. Next slide, please. Now, our experiment is to vary the molar ratio of those two, of zirconium chloride to acetic acid, because in the synthesis of the sulfonated UIO 66, they mentioned that they included acetic acid, although they never really stated for what purpose. So we want to vary this ratio and see, among other things, what impact it may have on its surface area. So is it a modulator, or is it something that just helps the binding process or something like that? What is its purpose? We don't really know. In fact, I think the paper was published April of this year, actually. So very, very recent. So our research is cutting edge, I guess. And essentially that's what we want to do, is see how it when you vary the ratio, how well does it absorb methylene blue? That would be like the last step. Will I get to do that? Not really sure. Next slide, please. And so when we get our sample, or when we will get our sample of the sulfonate UIO66, one of the things that we've used in this lab to study particles is what's called an X-ray diffraction, or in this case, we're using a powdery substance, so it's X-ray powder diffraction. And it's used for what's called phase identification of crystalline substances, so minerals, inorganic materials, etc. And a phase in this context means essentially a crystalline solid with regular ordered repeating three-dimensional arrangements. I had to look that up because I was pretty confused myself. I'd never seen phase used in that way before. And the X-rays that are used in this instrument come from a cathode ray tube, and it's filtered to where it's just one wavelength. It's made parallel, and then it's directed at the sample, and they scatter in specific directions relative to the sample because of that filtering. It's only one wavelength, and it's in a regular arrangement. If it's not a regular arrangement, then again, it's not really in a specific direction. And we have this diagram here to explain what's called Bragg's law. And that's, I believe it says there on the image, that's when constructive interference occurs. And that's what we want. That's when constructive interference occurs, we would have an increase in intensity of the sample. I believe I also mentioned, essentially the whole point of this is to generate a graph where you have an angle 2 theta on the x-axis and intensity on the y-axis. And when you put a sample in, it has a series of peaks, and those series of peaks are unique to that substance or that phase. And the diffraction pattern can be used for a whole bunch of different things, like the grain size, the lattice parameters, etc. But I haven't really gone into that much. I've only used it just what exactly is this substance. Next slide, please. Oh yeah, this is an example of an XRD pattern, or X-ray diffraction pattern. Although it's not smoothed out, so there's still random background noise, but that is an example of one. And so the machine it's essentially hooked up to a computer, and it has a database of a whole bunch of different samples. So you can say, you put in your thing, and let's say if you don't know what it is, you can compare it to a whole bunch of different samples to see, all right, do these peaks match up at these exact points? And if it does, then hey, you have a match. Next slide, please. This is the other way, the next thing that we'll use to analyze our samples is adsorption testing. And the goal of that is to determine the surface area, which is one of the main areas of our research. And it can tell us the surface areas of for particles that have pores of many different sizes. There's 3 different categories of pore sizes. I think it's micro, meso, and macro, where microporous it has a pore with a diameter of less than 2 nanometers. Macro is 2 to 50 nanometers, and then macro, I think, is greater than 50 nanometers. The pores of it, the diameters of the pores of that material. And I think we'll get into that a bit later. Essentially, there's 2 different kinds of absorption, chemical and physical. The one that we're using, one second. I believe you're using physical absorption because it's essentially a reversible process, and that's what we want. We want to absorb a material to it, remove it, and analyze how much of it was absorbed to it. Here, 1 second. What we want to generate is what's called an isotherm, which you can see on that graph right there. And it tells us essentially how much material is absorbed given a whole bunch of different variables. And it fluctuates depending on the strength of the interactions of the substance. And you can see right there is something called BET theory that names the 3 scientists. And it can be applied to a whole bunch of different kinds of isotherms, something where it's kept at a constant temperature. And it can tell you, among many other things, surface area using the variables I provide. I think it's ST, total surface area. And the variables that you see there, I think are, let's see, the weight of the monolayer. Monolayer is which something I forgot to explain is we use nitrogen to adsorb to the surface because it's readily available and it strongly interacts with most things. But we use liquid nitrogen. It's essentially what most scientists use because it's easy to work with and all the variables are known, etc. And so that would be the weight. And then I think, yeah, that N with a bar over it is Avogadro's number. And then the molar mass of the absorbent. The absorbent would be, in this case, nitrogen. And then I believe the last one is the A, the cross-sectional area of the absorbent molecule. That's a bit more complicated. And this has actually been quite interesting because every time I haven't gotten a chance to use this on UAO 66, but we've run it with ZF8 and the data has been questionable. But I've looked into this. The BET theory isn't exactly the best for microporous materials, which is what we've been working with. And I think it's better for as I mentioned, the meso and macroporous materials. Reason why is I think it had like a negative y-intercept or something like that, which was essentially would mean like there's imaginary energy or something, which is obviously no good. But if you were going to use this theory, you would take the relative pressure ranges from, I think, about 0.05 to 0.3 and use that and you'd analyze that data to get the cross-sectional area based on all those variables I just mentioned. This machine is also hooked up to a computer that does the data analysis for you. Although it doesn't just use the BET method, there's a bunch of different other ones that it can use to analyze your data. That is something that we'll be using in the future, I imagine, because the data we've gotten has been not the best. Let's see. Any questions about this? So thus far. So the last diagram, like sound waves. Not really. Yeah, I guess there's 2 different waves, but not really related to sound.
Just curious, how is this lab set up? Like, is it an actual physical filter, or is it more like a substance you put in and then you have to extract it somehow?
For which one?
Wait, the
Xray thing or the absorption testing?
The absorption testing.
Yeah, we have to put it, it's in this special, trying to figure out what to call that thing. It's like a glass rod and it has like a little tiny cylinder at the end. It's pretty expensive, or so I learned. And you have to filter in a specific amount and you like screw it in. The machine is pretty big, actually. It's kind of hard to explain unless you actually see this thing in person, but you screw it in. I think you attach like a heating thing to it along with the liquid nitrogen, and the machine takes it away from there. Once you set it up, you don't have to do a whole lot.
She never looked at it. Like it says data analysis at the top of it. Okay.
因为我只看着分，你在打电还是在上就是。
Okay.
Do you have a question? I guess not.
Sorry, Joshua, I muted you. I wasn't sure if you were trying to ask a question or you just came unmuted. We're getting a lot of background noise with it.
My bad.
No problem. Did you have a question?
Oh no, not right now.
Okay, just checking. Thanks.
Let's see. 1 second. Honestly, that's pretty much it. That's all I wanted to talk about, because the next slide is just all the different scientific papers I used to get all this information. So
You don't need the next slide.
I guess you can show it, because it's just a bunch of different.
Your sources. All right, hold on here.
Because like I said, once we actually synthesize the sulfonated UAO66, we can then run both of these analyses. And thankfully, when I finally get to do that, I would have had the XRD pattern to show and the isotherm to show. And I would have talked about, oh yeah, here's how the surface area changed when we varied, blah, blah, blah. But it's just a theory essentially at this point.
Gotcha. Anybody have a question? I have a question, Nicholas. So it sounds like you said this paper just published in April. So this is like really, really cutting edge stuff, obviously not in a textbook, stuff like that. So you said you applied for this project at first when you were a freshman, but because of COVID and that, it's delayed. So, would your advice be to the attendees today? What's more important that did Dr. Lay expect that you have some, knowledge and skills before starting the project, or just that you're willing to learn, kind of fly by the, whatever might come up, because, this is so new. It's like, it's really, maybe there's nowhere to learn it at this point.
Definitely. That's kind of what science is all about, actually. It's exactly that. Just learn as you go, because there could always be some new discovery or whatever, and it changes things.
Yeah, okay. Because I think a lot of students think like, oh yeah, I can't do research because, I don't have any, experience or things like that. But what I think really happens a lot of times is that faculty and researchers are just looking for students who are really willing to learn something and kind of, I'm sure Dr. Lay gave you some papers, read these and you can kind of get an idea of what's going on, and then, let you play around with some of the equipment, or, if it's really expensive, maybe watch what's going on, or, you kind of build your way up, to that kind of thing. So I would just say to the students, don't worry if you, never had experience, because a lot of this equipment is not a lot of people have worked with this equipment before. So it's just the ability or the willingness to, take on the challenge, basically.
Yeah, that's exactly it. When I first applied, I didn't have any research experience whatsoever. So in the, what was that called? We had to submit a resume and something else. What was that something else?
A letter of interest or something like that?
Yeah, something like that. And in that, I essentially talked about what you were talking about, was how passionate I was, how much I wanted to participate in research. And so if I was given an opportunity, what I would make of it, essentially. So that's what you have to
Yeah,
essentially
that's the really important part, because like you said, some students get interested in something because they're like, oh, that looks so cool. But when they actually figure out like it's all this work that you might spend a week on an experiment or something, set it up, and then circuit gets fried and the whole thing is, you have to start over again. So it's kind of having that passion to be able to, face adversity and, when you run up against problems, like think of something new. So I think that's an important thing to have as a researcher. Sorry, Josiah did have a question you put in the chat about the structure. Would it react with only the subject molecule, or do you need to filter out other molecules to prevent interference?
I'm not 100% sure, but we definitely do not want any contamination, because it does have this like sulfur group attached to it, which has all these charges. So if anything else got in there, it could screw the thing up, I'm imagining. The more charges things has, the more it could interact with something, essentially. So we do definitely want to filter out things to prevent interference.
So when you get to actually try it, yeah, like these are the things you'll find out. Like if,
exactly.
something's getting in there, like how is it happening and how can we prevent it? So that's a good question. Thanks, Joshua. Or Josiah, I'm sorry. Anybody else have a question for Nicholas? All right, well, let's see if I still have this. Okay, so I just in the chat put a link to the Summer Community of Scholars program. So are any of you planning on attending UAH this fall? Are any of you newly admitted students? George, okay, good. All right, well, if any of you are, this what happens is that you should keep your eye on your UAH email, and it kind of varies when it happens, but sometime around September, October, Tyree, good. You'll see a call come out and it'll say, well, actually to the faculty it goes out. It might be a little bit later, maybe October, late September, October. But you'll see an email that says, okay, all of the projects are listed in, now you can go and apply. And basically we apply through Charger Path, which is through the Career Services Office. And you can apply for as many of these as you like. And like Nicholas was saying, you have your resume and then like a letter of interest, it's called. So you're basically, telling the faculty member like why you should pick me. And another good thing to do, I don't know if you did this, Nicholas, is to actually reach out to that faculty member, and you can exchange emails, or sometimes they'll say, yeah, come and let's talk, because they kind of want to know, like, usually there's between 3 to 10 students that will apply for one project, but the faculty is going to pick one person to work with over the summer. So it's really helpful sometimes if they can put a face with a name, or they've met you or heard your voice, things like that. So and then anyway, we make the decisions early in the spring, and then you start work in late May, early June, all the way through the end of the semester, which is next week. So yeah, it's a really nice opportunity. And as a freshman, it might be a little more difficult to be accepted, just because you don't have as much of a what can I say, academic background built up, but lots of students do it. So I think it really depends a lot on that personal statement, letter of interest. So think about that. But if you do have some experience, doing things like this, I know there's, maybe some AP courses that have something, or other projects that, you may have done in high school that might be useful. So you feel free to draw on those.
Yeah, I didn't have pretty much any experience when I applied. I think it was the only the experience I cited was the honors 105 class I took. I think it was Intro to Research, which was somehow was tied directly to that. So I said, oh, look, this is my research, essentially. Is it sort of? But I made it seem that way.
Yeah, and it's hard to imagine, but like at some point, Dr. Lay was also, probably an undergrad who had no experience in a lab, but probably same thing happened. He worked with some professor, something like that. So, being smart is important, of course, but like I said, a good researcher has to be more than just, smart. They have to, be able to take on those kind of, problems as they pop up and be flexible and things like that. So anyway, it's really fun, and you don't have to do it through the summer program. I mean, that's, kind of one of the official ones, but a lot of students, just do it voluntarily. They work with faculty members, or you can do it through a class. Sometimes there's opportunities. And there's lots of entities in the area here. If you're from Huntsville or you're going to be in Huntsville for attending UAH, we have NASA is right here, Redstone Arsenal, Cummings Research Park is right across the street. So, tons of opportunities even outside of UAH. And then there's NSF REUs that take place all around the United States. So, Nicholas could maybe now, apply to one of those. He's probably excited to stay in the lab where he's at because he gets to focus on the thing he's been working on. But there's so many opportunities, but it's really a student initiative driven kind of thing. It's not like I can decide, Tyree, you're going to work with this person. It's sort of, we create these programs or we can give advice, and we're happy to look at your applications and things like that. But you really have to put yourself out there and apply for these things. But lots of really cool opportunities out there. And the nice thing about UH is you can get involved as a freshman. Are you in an academic club, Nicholas?
The American Institute of Chemical Engineers.
Okay, so I recommend too, like there's a bunch of different kinds of clubs. Some are like social focused and some are special interest. The special interest and the academic clubs, a lot of them have to do with like the majors that you're doing or you're interested. You don't have to do it in your major, but so yeah, this one that Nicholas is talking about, the nice thing is when you join the club like that, there's some social aspects. So you get to meet other students who have similar interests to you. And there's, upper class people in the club also. So some are probably already doing research, or this club might be open to graduate students. I'm not sure, and there's usually a faculty advisor for the club. So it's a really good way to get exposed to that interest and maybe where some opportunities are. So that's another thing I recommend for freshmen. And then the last thing is that the summer program that Nicholas is in now, we're going to have a poster session in the fall. And it's not 100% decided at this moment if it's going to be a face-to-face poster session, but I just actually was talking with Dr. Vogler and thinking maybe we could do it outside, which would eliminate a lot of the issues like with COVID and stuff like that. So anyway, that's going to be about the second week of September. So that's really good because you can come to that and you can talk to Nicholas directly, and probably Dr. Lay will be there as well. And Nicholas is only one of 40 students who are doing research this summer. So there's all kinds of other projects. And so you can see a poster and talk to the students. So that's a really good way to find out more as well. So anyway, that's all I have. Nicholas, anything else?
I would agree with you about emailing professors, because I have two different things about that. I think it was after the RCU program fell through, I just asked Dr. Lay, hey, is there anything I can do in the lab, right? And there was, and I shadowed a graduate student. And that is a great thing to ask if you're like into research, is find a professor whose research you're interested in and just ask them that, like, hey, can I shadow one of your graduate students because I'm interested in such and such that you are researching. That is something I would absolutely try to do.
Yeah, and that's great strategy right there. I don't know if you learned that from me, but I usually tell students, because if you go to a faculty member and say, yeah, I want to work in your lab, they'll be like, well, I don't have any funds available and my lab's really crowded. So that's kind of a hard question to ask, where if you say, hey, do you mind if I observe what you do in your lab, or could I have a lab tour? And then like Nicholas said, could I shadow like a grad student? Because grad students are, under the faculty member, so it doesn't, faculty members are really busy, so they're like, oh, I don't want another student following me around. So yeah, my grad students, you can, and they do a lot of the, hands-on heavy work in the lab. So they're great people to learn from, and they're, closer to your age. Basically, they're more like your peers. So those are really good strategies. Yeah, not saying, hey, I want to be funded in your lab, but just show your interest. And then probably Nicholas found that he kept coming back every week to shadow the grad student. And then that shows Dr. Lay that, okay, he's serious about it. He didn't come one time and then, he's gone, which is okay. Like if you do it and you're like, okay, this isn't what I thought, that's fine. Say, thank you, Dr. Lay, that was really interesting. And, and that's it, right? But if you keep coming back, then Dr. Lay knows, okay, yeah, this student really is interested in this and willing to put in the time, even though, he's not really doing anything. So we'll give him some work to do. He can kind of start getting familiar with the lab. And then at that point, Nicholas has been, working there, volunteering there for a while. So Dr. Lay says, he already knows what's kind of going on. So he'd be like a really good person to pick for the, funded position that I'm going to apply for. So, you kind of get your toe in the door, and then you just, keep going forward, basically, if you're interested. And if you're not, then, good thing you found out your freshman year that you don't want to be a chemical engineer. It's like, oh yeah, I thought it was going to be something different. And you might change slightly and going into electrical engineering or mechanical or something like that. So yeah, really good advice.
I also agree with trying to meet with the professors before the RCU program, or the ones, because I don't remember when it's posted, but there's like a whole list of different RCU projects that you can read, and you can apply to a whole bunch of them. And the professors that I met with beforehand were the ones that accepted me for their RCU programs. And so it's definitely a major help.
Yeah, I think students would just think, well, if I apply, that's good enough. But you're just a name on a list, right? Where if you're a name on the list, but they're like, oh yeah, Nicholas came to talk to me. That's right. He called me, or we Zoomed, or, he came to visit my office. Then they put a face with a name, and they're like, okay, yeah, that they have some idea of who you are besides just what they can read on paper. So yeah, it's all about putting yourself out there, which, again, it might be a little daunting for some people, but, my experiences at our faculty and research, people are really nice. I mean, they're extremely smart, experts in their fields, and you might feel afraid because of that, but, they're people too, and they're really nice. So as long as you're polite and do it, the right way, and don't rush them, and, you'll be fine. All right, well, I'll let you all go now, but thanks for coming in today, Nicholas. Thanks a lot. It's nice to hear about your research, so I'm looking forward to the poster. And again, if you guys can come to the poster session, I'll actually, when we set the date and time, I'll send it out to everybody. And regardless if you're a UH student or not, if you can stop by and see it, I highly recommend that. So, all right, thanks again, everybody. Have a good rest of your week.
Bye.
See you.